So let's grok RoPE, which is rotational or rotary positional embeddings. And this was a technique that first appeared from a Chinese lab, and actually it's very funny because the first explanations were all in Chinese blog posts. So back in 2021, I think Ulither AI was the first one to actually explain the thing in English, and I didn't understand it until now when I watched this really great video by Dominic Rompas, his name is, I believe, where he explains it in an intuitive way in a 3 blue 1 brown mat, MIM, whatever his framework is called, representation. So shout out to him. And now in this video today, I will be doing it on the whiteboard, all of the derivation, hopefully, so that I can try to give some intuition, and mostly just so I can solidify my own understanding. So let's start off with a important equation for RoPE, which is W, I forget what the Greek W is called, WK equals 2 to the power of, actually not 2, theta to the power of 2k divided by d. So in order to understand this, we will first need to discuss dimensions in a transformer, as well as 2D rotation matrices, which allow us to rotate pairs of pairs of values which represent our input token vectors in the transformer. So of course in our transformer we usually represent the residual stream as x, which is of dimensionality s by d, where s is the sequence length and d is the model dimension. So if you're looking at a GPT-2 style transformer, d will be 768, if I'm not mistaken, that's the model dimensionality, and then s, depending on your GPT-2 small, medium, large, whatever you pick, will be, I guess, somewhere between 512 to 8096, one of those values, one of those powers of 2. So let's keep this in mind to start off. And now let's map this to these variables here, because right now you see this right on the whiteboard, but you have no idea what it means because I have not explained it yet. So first of all, the d here maps 1-to-1 to the d here, which is to say this is the dimensionality, and we're going to use toy numbers in this entire video today, which means that d, let's say, equals 16. Okay? So literally our x input vector is of model dimension 16 and let's say sequence length 4. So we have a 4 by 16 residual stream, which could represent I like to eat, if we give it a word corresponding mapping. And each of these vectors is a token that, once we embed it in the embedding table, is of length 16. So we haven't really talked about anything to do with rotational, positional, and rotary positional embeddings yet, so I am apologizing for that. But now we will start, first of all, with the 2D rotation matrix, which is, if I'm not mistaken, cos, sine, negative theta, theta, sine, theta, cos, theta. So we'll see whether or not I'm wrong, because we're going to do a 1-to-1 example, because we love to get intuition from literally putting the numbers in the formula. Some people, unfortunately, are stupid and just try to understand the abstract formula without plugging in numbers, and they do not get the same intuition. I'm sorry, they don't. So let's look at a vector on a 2D plot, which is of coordinate, I guess it's a coordinate vector since it's 2-dimensional, which is of dimension 2 and is the following vector, so 1, 0, of course. And we want to rotate this 180 degrees, which gives us negative 1, 0, right? This vector here. Okay? And in theory, if we plug in pi, because pi is equal to 180 degrees, because pi is in radians, then this matmul should give us negative 1, 0. And this is why we're going to check, because I could have forgotten the formula, so let's do it. So 1, 0, right? First of all, to check the dimensionality, the 2 by 2 by 2 by 1 gives us a 2 by 1, which is good because when you rotate a vector, you do not change its dimension, you just change its magnitude. And actually, you don't change its magnitude, you change its direction. So if we have theta here, let's first calculate cos theta and sine theta. So cos theta is -1, right? And sine theta is 0. So this one is -1, this one is 0, this one is 0, and this one is -1. So I think we have the right matrix, because if you take this column vector multiplied by this row, you get -1 as the first entry. And then since 1, 0 times 0, -1 is 0, then you do end up with -1, 0. So this is the 2D, literally it's called the 2D rotation matrix, which is equivalent to rotating by pi radians if you set theta to pi and multiply by the given 2D vector. So you can try this with another example. Feel free to do that. So why is this even relevant? Let me explain why it's relevant. It's because rotary positional embeddings use k divided by, how many? It will use d divided by 2D rotation matrices to rotate each 16 length vector in this example. And I just mentioned a bunch of variables with no context, so let's dissect this into pieces. So first of all, one evident truth is that a 16-dimensional vector can be split up into 8 two-dimensional vectors, and then these 8 two-dimensional vectors can be multiplied by 8 2D rotation matrices. So what this means is that we need, for a 16-dimensional model dimension, because while this isn't obvious nor automatically true upon which dimension we're going to rotate, let's just take it given for now. I don't even think I'm going to motivate this. This is just a given that we rotate along the model dimension, and then rotate each token independently along its model dimension. So with this being said, once again, we need d divided by 2D rotation matrices. And just for a final time, this is because we have 8 of these for a 16-dimensional vector, so we need 8 of these. And now we can start to look at why we have this 2k divided by d. These 2's are not also there by coincidence. So let me explain. First of all, a 2-dimensional vector is in a 2-dimensional subspace, which means that this matrix is rotating a 2D vector. So this gives us the exponent here. So why does it give us the exponent here? What this is saying is, first of all, there is an implicit for loop here. It's saying for I from 0 to k, do this vector, right? So wk I didn't mention, but it will give us a vector, and I'll give you an example so that it's clear. But in essence, we have k two-dimensional subspaces which we rotate. And k is equal to, once again, d divided by 2. So this should be crystal clear by now. If it isn't, I'd recommend to go back a few minutes and rehear what I said. So there are k two-dimensional subspaces with k equals to d divided by 2. And for each two-dimensional subspace, we calculate theta equal to the radian rotation. Because what will become evident soon is that when we have our individual 16-dimensional vector, we will rotate each pair 8 times, and each pair will be rotated by a different theta. And immediately let me make this clear, that this different theta we rotate is in order to be able to encode both long-range and short-range dependencies in our vector. How so? It's because theta will, I'll show you, get from a large value to a small value as we go down the embedding dimension. So I'm trying to think of this actually right now to myself in an intuitive way, because maybe I misspoke about the long-range dependencies. Maybe it's a separate part of the RoPE that allows for this. But essentially what I'm trying to say is that the initial the initial values of this vector will be rotated much more, and the later values that are deeper in the embedding dimension will be rotated less. So I think I lost intuition as to why this helps, but maybe I'll remember. Anyways, that is a quick aside. Now let's get back to what we were saying, which was about theta here and the fact that this is actually a column vector. So because there are k two-dimensional substages, k equals 8, then this means that since our for loop iterates over 8 values, that wk is an 8-dimensional vector. So actually wk is a specific value of k. That's why we have it not represented as a vector. But once we take out the w, then we now iterate k times over it. And we have k equals 8 because d equals 16. And if we just iterate through k with, now we have k, we know it's 8, and d equals 2, so it's equals 16. Then for the first value, we'll get 0 divided by 16 equals 0. We'll get 2 times 1 divided by 16 equals 1. Sorry, 1 over 8. Then we'll get 2 times 2 divided by 16 equals 4 divided by 16. And this is 1 over 4. And then this will go all the way to k equals 8, giving 2 times 8 divided by 16, which gives us 1. Okay? And then once we have 1, we just have theta on its own. Okay? One thing I just totally forgot is that either you can mention this, or either you can put a negative sign here, so you have the reciprocal, or it's also commonly just represented as 1 divided by the theta, but I prefer the negative exponent approach. Okay? And so what this means is that in this vector, w, or omega, I just remember this is the name, you have, for example, theta to the power of negative, at the beginning, negative 0, if I'm not mistaken, right? Because k is 0 for the first value, so it's just 1. 1 radian of rotation, if I'm not mistaken. And then, yes, because this is in radians. And then for value 2, we have theta to the power of negative 2 divided by 16, or negative 1 over 8. So it's the 8th root, negative 1 over 8. The 8th root of the reciprocal of theta, and this just goes down. And we'll talk about how these values progress, but just have this in mind that this is essentially omega, the vector of radians in order to rotate the 8 pairs in the proper way, which is to say that each pair will be rotated by a different amount. Because if you now think about it, right, if you rotate the entire vector by the same radians, then you do lose some granularity. You kind of give the model less granularity and less stepwise transformations to integrate into its learned parameters. Because let's consider another example in a neural network, right? If you introduce a nonlinear activation function, you're essentially allowing the neural network to model nonlinear relationships. And although there's no linearity, nonlinearity in this instance, you are just giving it like a gradient of dimensions to add and represent its data in a more rich way. And one thing that I just realized is that I do have the values for this exact calculation. I'm trying to think, okay, it's in my Python terminal right now. There's no way for me to show you guys this without writing, so I think I'll just have to write it. So I'm just going to round them, but of course the first value is 1, as we said. Then we have 0.2, 0.06, and I'm just rounding these, 0.01, 0.003, 0.0007, 0.0001, and 0.00004. So one thing that it is really unintuitive to consider the numbers in this sense. Therefore, you should instead convert these to degrees in your head. So, write what's pi over 2, for example. Pi over 2 is approximately 1.5, which is 90 degrees. And if that is true, then this one is approximately 60 degrees. And if you want, you can go through the rest and convert those to degrees because it is more intuitive. So like, you can see that we're already like by the 8th dimension at a very, very small degree. But one thing that you need to know is that this is only for the first, sorry, not the first, but if we index from 0, it's from the first. If we index from 1, it's from the second value in our residual stream vector. And why is this the case? It's because one thing I didn't mention is that essentially, if we represent these all as x0, x1, x2, and x3, of course, we have these residual stream vectors, and we need to rotate them. Like, you have to rotate them. You can't just make up this rotation vector and then just have it. You have to actually rotate these vectors, which will eventually be represented through a matrix multiplication. But right now we can just think of it abstractly as you'll multiply this, this token, which is part of the residual stream, by omega applied to this 2D rotation matrix. But now let's just forget all that I said. We'll rotate it. So let's just say we have R1, R0, R1, R2, R3. And these are the abstract rotation matrices, which will rotate the entire vector. But one thing you need to know is that all these are the same except for a factor. So instead of this, you should do R times 0, R times 1, R times 2, R times 3, with the value, the number being the position of that token in the sequence. This means that R times 0 is 0. And if you multiply this matrix by that, then you're applying a rotation of 0 degrees. So it does nothing. And then R times 1 is just this exact matrix, this exact vector. So you're applying this exact rotation. But then where it gets interesting is that at token 3, you multiply this by 2, such that now you rotate this one by 2, 0.4, and you can see this pattern go all the way down. So in fact, the second matrix, right? The third word, why did I say second matrix, will be rotated in the first 2 pairs by 120 degrees. And now you can see that this rule will make it such that as soon as you get to a larger sequence number, then you'll start to actually rotate, essentially do a complete modulus rotation. And this is quite interesting because if you have like a million token context, then these first two pairs will rotate a lot, and it will kind of confuse the model because you're obviously congruent modulus 360 degrees or congruent modulus 2 pi. So you can't really, you lose some of this positional encoding when you do this. And this is why in a long context model, you use a large theta. And why do you use a large theta? Let me first tell you that 10,000 is the default theta in most settings. But now, in larger models, you're getting thetas of 100,000 or even 1 million. E to the 6. And why is that? It's because if we increase theta here, let's look at what happens to the formula. So 10,000, which is theta, to the power of negative 2k divided by d. So we have to take a value so we can actually see what happens. Let's just do k equals 1, which would be the second pair in this. Where is our vector of 16? There it is. So it wouldn't be the first pair that would take that theta. It would be the second pair. So it would be the elements 3 and 4 in that vector. And then right? That will be 1. So it will be 2 times k, which is 1, divided by 16, and then the negative this. So it was negative 1/8. Or, equivalently, 1 divided by 10,000 to the power of 8. Sorry, not to the power of 8, but to the root 8. Okay? But now, if you have theta equal to 100,000, then it'll be 1 over the 8th root of 100,000. And what this means is that these values will be smaller, right? Because you're dividing by a larger denominator. And therefore, as you scale the series, then your increase in rotation as you increase the sequence length will be less. And therefore, if you have a very large context window, then you will have less congruent rotations, which will essentially start to overlap and lose positional information from. So there's that tangent on theta and its role as a hyperparameter. And we also discussed that you have this vector of 8 rotation thetas, essentially a theta which represents our rotation, which must then be multiplied by the position of our token in the residual stream. Once again, this means that we apply a rotation of theta equal to 0 here because we just multiply the rotation matrix by 0, and it doesn't actually zero the vector because if you take the 0 of these thetas, then it gives you, what does it actually give you? So cos of theta is 1, negative sine of theta, which is 0, is 0, and then this is 0, 1. So it gives you the 2 by 2 identity matrix, which will just return you the original vector. Okay, so this is quite good in terms of the initial motivation. Now, like we haven't really rotated anything except for representing it in its abstract form. So let's actually represent it in a concrete form. I think that's the next logical step here. So we want to keep this very intuitive list of 8 values, which represents the radians that we rotate each vector by, each pair of vectors by. And I think, yeah, we're ready to now talk about the dimensionality of the vectors in this rotation process. But let me backtrack, in fact, because I just realized we can talk about where this fits in the entire transformer model. So let's talk about the transformer block, which is in the standard implementation a multi-head self-attention. Right, we have our layer norm before this. Depending on if you're doing post or pre-norm, so ln, let's assume that we're doing pre-layer norm, and then ln, and then actually, I think we only do the layer norm between a collective multi-head self-attention and the MLP. Luckily, I have a poster of the transformer right here, so I can look at what it said. Okay. Okay, never mind. So after the MHSA, we do a added norm, and then even after the feeded forward, we do added norm. And here it has the cross tension, but we're not even doing that. Interestingly enough, they do post norm in the original transformer, but I think it's actually the later transformer methods which use pre-norm because it allows you to have a deeper transformer network, which is to say more transformer blocks. So now that we know that, let's redraw. Okay, so we have the pre-norm here, and then we have the skip connection here as normally, and then we do the same thing. So why did I draw the layer? Oh yeah, because we have the layer norm pre-norm before our MLP layer, and then we also add the input of this to the output of that, which is called the residual stream, skip connection, residual connection, whatever you want to call it. But now we have to add in this step. I don't know if it's before the layer norm or not. It's not really that important to know. I mean, it is, but for a high-level implementation, it is actually necessary for implementation, but for high-level overview, it isn't necessary. It's at this stage where we want to apply our RoPE. And let me motivate why. Because in fact, whereas in an absolute positional encoding, which is also somewhat similar in the fact that it uses sine and cosine throughout the rotation, it's actually not a rotation, it's just a shift for each position. I honestly lost some of the implementation details of classic absolute positional embeddings, which have a similar formulation, but it's not actually rotating the vectors, it's just adding a value to each vector. As opposed to that one, which actually happens right after the tokenization, or in essence during the tokenization, you just add the absolute positional embedding to the initial vector which you calculate from the embedding table. As opposed to that, we do this before every single attention call, and to understand why, it's because I'm trying to think why. Kind of lost the reason for that. But once again, I'd recommend to watch the video which I've linked in the description on attention, not attention, but on RoPE. So we do this, and we, in particular, right, you do Q, K, T, V. We want to rotate this matrix because this is what's giving us the attention scores, whereas the V matrix multiplied by the attention scores is just a linear weighting, or a weighted average over our attention scores in order to essentially select whichever values we want to attend to. Okay? And what this means is that, yes, we applied at that stage, but I'm not going to go into any more detail on that end of the spectrum. Let's go into like the actual calculation itself, which is to say the actual rotation of the matrix, and then see how that is motivated. So let's look at the dimension of our model. So I'm just going to write down some numbers which are not going to be immediately understandable, but will be in a sec. So, right, this, and then in fact, this is a 1. So what does this mean? Let me explain what this means. So, okay, so this is the matrix of the residual stream. And why? Because I told you guys it was S by D, but now I have 5 values. It's because we of course have a batch dimension in a transformer, but it's just 1. So you could just squeeze it out, but we'll have it here just because that's how it would be represented in a transformer. Batch is equal to 1. And then we just doing single, scaled dot product attention, not multi-head attention in this case, but you could represent this as multi-head attention simply by making the head, for example, 2 in this case, and then maintaining the sequence length, but instead folding the head dimension into the sequence dimension, and then making the model embedding dimension 8 by 2, which is actually the case right now. Why is it actually the case 8 by 2, even though we're doing single head dimension? In which case you would have a 16 dimensional vector doing that calculation. Let me just text my mom so that she doesn't interrupt me. I am recording a video, by the way, so please don't interrupt. Okay, so damn, it's only been 30 minutes. So let's wrap this up here. We have 8 by 2 by 1. Why 8 by 2 by 1? It's because once again we need 8 pairs of 2 elements to rotate. Right? We need to split up our 16-dimensional vector into 8 pairs of 2 elements. We motivated this already. And then this vector, this matrix here, right? It's just 8 2D dimensional rotation matrices. So actually, I think really at this point, you understand well where these numbers are coming from. And how do you get the 8 rotation matrices? I didn't actually mention this. So once again, you have cos, negative sine, sine, cos, theta, 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 theta. And you'll stack 8 of these. So you'll stack 8 of these. And for each of these 8 2D-dimensional rotational matrices, you will multiply this by the corresponding theta. So in this case, if we're concerned with the second token in our 4 sequence length vector, then it will be multiplied by 1 for the first 2 pairs, 0.2 will be the second matrix, which will rotate at 0.2 radians, and we continue on. So this is how we get our 8x2x2 matrix of 2x2 rotation matrices. And then let's do a single calculation to understand what's happening. So when you're doing a matrix by matrix multiplication with more than 3 dimensions, you can just ignore the dimensions which are outside of the innermost 2, because those are just, I forget how it's described mathematically, but they're essentially, non-rotation dimensions, so they're not included in the actual matrix multiplication. But these 2 are, and we get a 2x2 by 2x1, which once again gives us a 2x1 vector at the end, which is what we want. So we'll just put it back here, and then we'll squeeze this dimension back to be 16. And I forget if it's squeeze or fold, or how you go from a 8x2 to a 16. I forget the PyTorch term. I know one of them is squeeze, and I think the other one is unsqueeze, actually. So I think unsqueeze is to get to 8 to 2, and then squeeze is to get to 16 from 8 to 2. And what you will notice, right, is that this was 16 before, and then it became 8 by 2 by 1. So first you have to convert to 8 by 2, and then in order to be able to multiply these 2 pair vectors, we have to essentially add this extra dimension here, which represents nothing, right? Because what is this actually representing? It's a 2 by 1 matrix, so x and y, and then we just add dimension, because instead of it being represented as a row vector, it should be represented as a column vector if we're multiplying this matrix on the left. Actually, that's really poorly explained, but let's just get on with the calculation. So we have cos theta, negative sine theta, cos theta, multiplied by xy. And we actually already motivated this before, so no need to really go over it again. But in essence, in essence, what's happening here is that we rotate these 2 pairs, and then we'll put it back into the matrix here, which represents our token in the residual stream. Okay, so we've rotated every single pair. We do this for every 8 pairs that exist. So if you think of this as the first 2 pairs, they're rotated from greatest rotation at the top to lowest rotation at the bottom, and then as you go to the right in the sequence, you also increase the rotation degrees. Okay, so have this in mind. And then once this is done for a single vector, then we'll do this for the other vectors, of course. And then what's happening actually is that you can represent this in a more efficient way, which I'll just describe now. But before that, how does this give us the end product? We rotated now these pairs 2 by 2, and then we'll now collapse this into a 1 by 1 by 4 by 16 matrix, which is just 4 by 16, which is S by D. And then we'll just pass this on to the attention calculation with these rotated vectors. And not only will we pass this on to the attention mechanism, I need to specify that it's done directly before we multiply the QKT matrix. So we take, I think it's actually represented, RoPE of QKT, and then you'll softmax that, or then you'll divide it by, I don't know if you divide by the dimension of K, the square root of the dimension by K before or after the RoPE, but it shouldn't really matter since there's independent operations, or they should be commutative operations, and then you'll softmax that. What else is there to say? Well, I haven't even mentioned the one optimization that is done in any code implementation. So you have 1 by 1 by 4 by 16 at the end, but how's a more efficient way to get to 1 by 1 by 4 by 16? Let me show you here. You will take the fact that, all right, let me represent this as RoPE. Okay, so RoPE is the 8 by 2 by 2 matrix, and then X is our 8 by 2 by 1 matrix. RoPE X plus RoPE X equals rotated vector X. Okay? So what multiplication am I talking about here? Am I talking about a matrix multiplication? No. I'm talking about an element-wise multiplication of a matrix. So what I mean is that you'll take this RoPE matrix, which is 8 by 2 by 2, right? You can think of it as 8 2 by 2 matrices on top of each other, which is then no longer even 3D. It's just a 2D 2 by 2 by 2 by 2 by 2 matrix. And then we'll take, for every single matrix, the row, which we'll just denote this by dot. So we automatically take every row, and then we take the 0th column of every row, and then we multiply this by, for our 8 by 2 by 1 matrix, the same row and the 0th column of that row, and then for the second component, right, because we want to get from this calculation a 8 by 2 by 1 matrix at end, then we want to get the second value of the pair, which would be equal to y, which will be every row, the second column, which is 1, that represents y, multiplied by that same value, dot 1. And why is this? Let me represent this in a diagram, okay? Let's delete 8 pairs of 2 elements to rotate, because we don't need that anymore, and we'll also erase the 16-dimensional vector, because that's already been explained. And now we will explain how we can optimize this matrix multiplication, which would be many small matmos, which would call many kernels, which would take up many communication primitives, whatever. Instead, we're just going to do this as one single addition of 2 element-wise vector multiplications. So why is this possible? It's because when we do I keep on writing this and then erasing it, so that's L. When we do this multiplication, right, we end up getting x times cos plus sine times cos, sine x times cos, sine times x, right? I have essentially obfuscated the thetas here, and then sine theta times y, cos theta times y. So you can notice here is that we multiply x by every single element of the first column, and we multiply y by every single element of the second column. And then in fact, when we come back here, we realize that the notation is just a different way of writing the same thing, which is to say that we take our RoPE value at a given row, let's say row 0, and column 0, which would be like cos, and then multiply this by our input vector x at row 0, column 0. And I just realized we call this a 2 by 1, right? So yeah, it is actually represented as 2 by 1. And then when we get to the second value, so now we're in the second row, which is sine and cos. I'm just trying to think how this would math, right? We would get the value for sine in row 1, column 0 from this, and then we would get the value for x in row 1, column 0. So intuitively, this would actually give us the third element of the vector, but we don't want that. So there must be some PyTorch simplification that's done in order to prevent that multiplication from happening. But I hope you understand that the high-level optimization here is the fact that we have x that's only multiplied by the values of the first column, and we have y that's only multiplied by the values of the second column. So we have like this kind of intelligent way of multiplying these vectors, then we can, and then adding the two results for the first column and the second column, then we can get back our pair of xy vectors, which are equal to the initial dimension, 8 by 2, and they are rotated now by the RoPE 2 by 2 matrices, which in fact we represent by this addition of the element-wise element-wise matrix multiplication. Okay, I think that's everything that I want to discuss for this intuitive explanation of RoPE. It's really high level, I just realized, because we haven't even discussed the code, but I would recommend to watch once again this video done by, I forgot his name, but the German guy. And yeah, essentially RoPE is using matrices to rotate vectors. In this case, a 2 by 2 matrix. One thing that you might be wondering is, well, why don't you, of course, your embedding dimension needs to be a multiple of 2, or else this won't work because you're rotating pairs, but luckily everything is powers of 2 in transformers, so it doesn't matter. You might be asking, okay, why don't you do actually, let's consider that you have a model dimension of 6, or even 768. Is 768 divisible by 3? 7 plus 6 is 13, 21. It is divisible by 3, it's 7 times 3. Okay, so 768 is a model dimension, and it is divisible by 3, so why don't you actually rotate pairs of 3 in a 3D rotation matrix, or a 3-dimensional rotation matrix? And the issue is that now you have to decide along which 3-dimensional rotation to rotate, right? Because if you have a vector in 3D space, if I say rotate this vector by pi, it's not obvious. Are you rotating it on the xy plane, on the zx plane, on the yz plane? So you have to decide. And this can be a learned parameter. So I'm sure that people have done this and have set the rotation dimension as the learned parameter, and probably it would give good results because now you're allowing deep learning to essentially learn what rotation dimension is the best. But when you do have a 2D dimension matrix, then you have no learned parameters in your rotation, which is good because there's already a lot of learned parameters in a transformer. And like, do you really need to learn rotations? Well, you can, because actually you can have learned rotation embeddings as opposed to any rotation, which is just adding a learned S by D vector matrix to the input at the very beginning after you tokenize and learning the positional embeddings. You could do that, but then you have less parameters as well, which isn't inherently a bad thing. So yeah, there you go. That was a ramble on RoPE, rotary positional embeddings. I spent the last day learning it, and hopefully this is helpful to one person at least.